All right, let's go ahead and get started here. We did not lecture on Wednesday, but we're gonna dive into it. Look at all you guys, you all showed up. The only problem with when this many people show up is it's really warm in here. I'm gonna start sweating through my shirt again, so it's gonna be really embarrassing semester. Sally, my sister, says hi with a heart emoji. She also said you're a terrible student and to keep my eye on you. So she did not say that. She did give the heart emoji. She did. So hello. You're very rare. It's happened once before. Somebody else that you were taught by two berries, siblings in your lifetime. Yeah, we'll see. Hopefully I can teach you something. I forgot to mention this last time. It may look like I have a popsicle stick taped to my finger, and it's because I have a popsicle stick taped to my finger. I didn't know you could do this, but I broke the tendon on the back of my finger. I don't know if you guys knew you could do that, but you can. You just rupture it straight through. And what I was doing, unfortunately, I wish I could come up with a better story, but I was making a bed. I was rage making a bed is what I was doing. So I don't know if you've ever had like a fitted sheet that pops off the corner of the fitted sheet. And it did that to me in the middle of the night. It popped off the corner and it kind of like went up over the side of my head. And I was furious and I got up and I grabbed it and I shoved it down around that corner. And in the shoving process, it puts a lot of stress on the back side of your finger and it popped right off it. So I'm on week like 6 with the popsicle stick taped to my finger. I went to a doctor, I had him take x-rays, and then I had the popsicle stick already on my finger, and he goes, that looks like that's working just fine, and he had the nurse tape it back to my finger, and it's been there ever since. I took it off the other day, and my finger was still super crooked, so I don't know if the popsicle stick is working, but I shook several of your hands a couple days ago, and I forgot to mention to you, like, hey, that is indeed a popsicle stick. I literally had my son eat a popsicle, and then I took the popsicle stick and I cut off the end and I taped it to my finger. So I'm a doctor, so I know what I'm doing. But it's strange. It's strange. Okay, let's get started. So what is dynamics, right? Let's go with this. All right, dynamics. What were the key equations in statics? What was the key equation you had in statics? There are two main equations in statics. What were they? What was the main principle in statics? Sum of the forces equal to 0. Yes, right? So statics, right? Sum of the forces equal to 0. Right, that was it. And then there was obviously there were some vectors and stuff in there. I'm going to try to be careful about notation and stuff, putting like the line over it, meaning that those are vectors. So that was one of them. What was the other equation? Sum of the moments, right? Sum of the forces equal to 0, sum of the moments equal to 0. When that happens, things aren't moving, it's static, hence the name statics, right? Like, just don't move. Stay right there, right? This is the world I live in, right? When we design buildings and things like that, that's what we want. Sum of the forces equal to 0, sum of the moments equal to 0. Dynamics, though, what are the forces equal? What's that? Yep, sum of the forces is equal to mass times acceleration. Right? And that's the big difference. Is now it's not equal to 0. Now it's equal to mass times acceleration. So we're gonna spend the whole semester working with this guy, and then the other one, the moment equation. I don't expect you to know this one. All we're gonna say is it's not equal to 0. Right? That's one of the last, it depends on if we're doing 2D stuff or 3D stuff. There will be moment equations involved. In 3D stuff, it's going to be the biggest equation you've ever seen. They're called Euler moment equations, but they end up being about half a page long. They're very large equations, okay? But this is what we're going to be spending the semester doing, is applying this equation and seeing how forces relate to accelerations and how accelerations relate to forces, and then there's velocities in there as well and things moving around. That's kind of where we're going to spend it. The structure of our course. So that's the key thing here. Right? That's the key difference. It's going to be equal to mass times acceleration, not equal to 0. Okay. So the structure of the course. There's three main components that we're going to look at, and these are we'll talk about the exams in here a little bit too. What's going on here? Give me I'm going to try to type when I can. Although I can't type with a popsicle stick on my finger. We'll see how this goes. I have very bad handwriting, so over the years I've done this. Particles, right? We're going to start out with particles. We need to make that a little bigger, huh? Yeah, that's 16. Okay, and particles. Oh my God, I'm having issues here. I can't type. There we go. Okay. Mass. Mass is concentrated at a point. Right. To what was done in your physics class. Right. You see, we're going to start out, what we start out with is these particles. You've seen this particle stuff before, right? This is what you did in your physics classes. Like you've done some dynamics, whether or not they were calling it dynamics, but you did it, right? When you derived acceleration equations and the velocity or the acceleration is the derivative of the velocity and the velocity is the derivative. You've done this stuff before. That's the physics. So we start out probably the first third of the class is kind of review, maybe a little more advanced because we're going to have acceleration function of velocity, acceleration function of position, things like that. That's got a little advanced, but everything starts out with these particles, just a single point flying through the air, okay? A single point with loads on it, right? Then we're gonna go to 2D rigid body motion. This is where things get pretty interesting. That's the next subject, all right? And the last thing we're gonna do is 3D rigid body motion. You know, if you're typing properly, the only letters that you use your middle finger for on the right hand are the I and the K. Just to let you know that. So the I and the K, I'm stabbing it with the popsicle stick. It's interesting. Just a little side note for you. Just if you were wondering how that affects your typing, that's it. Okay. Now, with both of these ones, sorry, the last two, the rigid body motion, we have distributed masses, okay, and the body is non-deformable, right? So we're gonna have to take into consideration, right? Like an example would be this pen. If I threw that pen through the air, it has a distributed mass, right? It's not concentrated like a bullet or a projectile. It has a it's distributed mass, and how that mass is distributed is gonna affect how it's like rotating and stuff throughout the air. So that's gonna be the distributed mass part of it. Okay, the rigid body part of it is we're going to assume that our bodies, as they're flying through the air, they don't deform. They stay in one shape, right? If you tried combining deforming bodies and stuff flying through the air with distributed masses, we'd start getting into like mechanics and materials at the same time. Something's flying in through there. So for most of undergrad, you don't combine the two. In grad level courses, you start combining them. Like, oh, something's flying through the air and it's deforming. But for this class, we don't do that. That's why we got the 2D rigid body stuff. So we're gonna the 2D rigid body stuff. Everything's stuck in a plane and moving in a plane. Then we get into 3D body stuff, and things are like kind of rotating around. That's where things get super weird in that realm. Your intuition completely gone when you move into that realm. Okay, so for each one of these things. Right, so that's kind of the main topics that we're going to do. Let me get that in there. Yep. For each one of these things, what we're going to do, have the same structure here as well. And what we have is, we're going to start out with a thing called kinematics. Kinematics is the geometry of motion. The other thing I really like to type for is I'm a really bad speller, and if I'm writing by hand, then you can see that I misspell stuff, but I just misspelled kinematics there, but it corrected me, and it doesn't matter. As I was going along, my computer corrected me, so if I type it, it hides the fact that I don't know how to spell. Okay. Kinematics is the geometry of motion. So we're gonna start out with the geometry of motion. That's what we're gonna start out with today. Then we're gonna move on to kinetics. forces resulting in motion. Right? How do we tie the forces to actual motion? So we start out with just geometry talk, then we're going to start tying in how those forces relate to it. When we start talking about how forces relate to motion, that's where it's called kinetics. Okay? There's three different kinetics types or methods we're going to use. One is going to be what we call FMA, force mass acceleration. We're just going to use Newton's second law. We're going to use that sum of the forces equal to mass times acceleration. Sum of the moments is equal to this big equation. We're going to solve them just using those direct equations. Okay, that's the FMA. Then we're also going to do work energy. Some types of problems are easier to solve with work energy. You may remember this from your physics classes. I really enjoy the method. I think it's a really powerful method, really cool method. And then the last one we're going to do is impulse momentum. Why it's making this so small. Okay, so just kind of reiterate what it is we're doing and where we're headed. We're going to start out with particles, and we're going to talk about kinematics first, the geometry of motion, no forces or anything at that point. Then we're going to do particles, kinetics, particles, force, mass, acceleration, particles, work energy, particles, impulse, momentum. Then we're going to switch over to 2D rigid body. Then we're going to do kinematics. Then we're going to do kinetics, FMA, work energy, impulse, momentum. And then we'll finish up with, right after Thanksgiving, we'll do 3D rigid body motion, kinematics, kinetics, FMA, and then we won't get to work energy and impulse momentum, but we'll make it through force, mass, acceleration for 3D rigid bodies. So that's the structure of it, okay? The way we have the exams, I don't know if we talked about it briefly in the syllabus. We have 4 midterms. The first midterm is going to be particles, kinematics, kinetics, right? Those kind of 2 main topics. There's going to be 2 problems that you have to work out. Then at the force mass acceleration, then there's another one, particles, work energy, and impulse momentum. That'll be another exam. Then we'll do 2D rigid bodies, kinematics, FMA, 2D rigid bodies, work energy, and impulse momentum, and then finish up with the 3D rigid body motion for the final. So that's where we're headed with all this stuff. Any questions about the structure of this? Where we're headed? Right. Seems a little daunting, but it's not bad. It is very, I've taught this class enough. I have it very structured. We just step through and just, the tools we learn from one, like what we learn from here will apply here. What we learned here will apply here. And we're just gonna stick to the plan and go that route. Where people really run into problems is like, I'm gonna give you a plan to solve, how to solve these types of problems, right? I'm gonna get a nice, beautiful plan. Where people run into issues is where they start making up their own methods, right? Or they're like, oh, I remember back my physics teacher told me to do it this way, and they try to do it that way, right? That's where people run into problems. Or like, oh, I got a feel for this. I know what this wheel is gonna do. Don't do that. Just stick to the plan. I have a nice, beautiful plan, right? You don't have intuition for this stuff yet. Right? You get intuition from being like deeply involved with the material for many, many years. You guys are not that way yet. Maybe the particles, you can kind of get away with some intuition, but right after particles, though, absolutely not. You can't do it. I mean, I've been teaching this class, like I said, this is probably like the 10th time I've taught this class, and I still have not developed any intuition for this stuff, especially when we get into the 2D and 3D stuff. It's weird stuff. Related, let me see. Yeah, okay. One second, I'm gonna look for something. I have my notes on my phone, by the way. I'm not just like texting up here, just an FYI. You guys are freaking me out. You're all quiet. Don't be so quiet. Okay, you can laugh at me, that's fine. You can make fun of me, that's fine. Just don't stare at me blankly. You're making me uncomfortable. It's not because it's hot in here, it's because I'm sweating through my shirt because you guys are making me nervous. Give me 1 second. I'm gonna see if I've got this. There you go. See, there you go. Talk amongst yourself for a second.
Okay. I have one every day. Yeah. I have like an hour-long break.
All right, okay. I gotta do it. I got it here. Okay, let me show you this one. I typically will bring. I have this wheel in my office. Okay, I have this wheel in my office. Right, and this is what I'm talking about. Like how I mean, by the end of the semester, the last example problem we do in class is really similar to this. It's very similar to this. So this is just a bike wheel. It's got been pulled off a bike, obviously. It's got a little axle that's sticking through there. And then in Trent, this is Trent, he's a former grad student. He's got a string there that's attached to the base right here, right under the side of this axle, right on the very end of this, right? So you know, in the statics world where I live, right? If he lets go of this thing, what's this wheel gonna do? It's gonna fall down, right? It's absolutely gonna fall down because I'm holding it there, right? And this thing, well, it's gonna fall down. But this wheel is spinning and it doesn't fall down, okay? What it does is it starts processing around an axis. It'll dip a little bit at the beginning and then it processes without actually falling down. This is what I'm saying, like my intuition would never say that this wheel would actually do this. It hangs there.
Amazing.
Hold on, oh God. My first time using a computer.
Wasn't spinning. Trey, my wonderful assistant.
I don't know how to turn it down.
Or show us something cool. Alright. Hang it by one. And it doesn't fall down. And
Isn't that weird?
Amazing.
I mean, just
If
that
it wasn't
anybody's like
spinning,
intuition be like,
so
oh,
what would
like
happen
it's
if
not
it
gonna
wasn't
fall
spinning?
down, obviously. Right? I mean, we use that concept a
Yeah, it
lot
does
in
that,
life, right? But like,
That's weird.
just to see it in that,
Okay,
to see it in that context is just so, it's so, and then like to feel it, like there's no tricks or anything involved. It just does that.
And it doesn't fall down. And it-
Not only does it not fall down, it also processes
If it
around. By
wasn't-
the end of the semester, we'll be able to mathematically show why that happens, right? Will we understand what happens? I'm still, like the 10th time I've taught it, I'm starting to get it. I'm just starting to finally like get oh yeah, that's what's happening. And I mostly got it, but mathematically I got it, right? I could show it. So that's kind of what, this is what I'm talking about. It's like your intuition, if you tried solving that by hand, you couldn't do it. So you just we have a nice, beautiful equations to follow, a nice procedure to follow, and it'll lead us to the solution that thing doesn't fall down. You know, the concept of this, we use it all the time, right? There's stability in something that's rotating, right? And that is why, you know, there's rifling in a gun, right? So the bullets, you know, get some spin on it so it travels straighter, right? What's another example? Gyroscopes, absolutely. Freaking spirals, right? Throwing spirals, dropping bombs, right? Like, fucking Tom Brady. I hate Tom Brady. It's ruined my life so many times, right? Rooting against those Patriots, but then, anyways, Tom Brady's throwing spirals, right? Like just beautiful. So we use that concept a lot, and like I said, mathematically we'll be able to show that later. Okay, so that's where we're headed. That's the very last thing that we're gonna do in this class is that example we just saw. I like to show that just so you kind of see where we're headed, and then you get my little spiel about don't trust your intuition because it's not going to help you at all. Okay, so let's start defining things. I stopped by the bookstore. There's still no book. Okay, I don't know what they've done. So track went down. Yeah.
When we went and asked, if it said it doesn't look like it had it doesn't have order in it, and they said maybe the professor just hasn't ordered them yet, and I was like, I didn't know the professor has to order them.
Yeah, I didn't either. And then, but I went over there about 3 weeks ago, and I had a talk with the head dude, and he went there and he sent the email to order the stuff because it hadn't been ordered, and so I don't know. We'll make it work. We'll make it work somehow. Somehow. Like I said, you may or may not be able to Google it. And then also, I'll post at least the first couple of chapters so you can have those to kind of follow along. So, okay. Okay, so then the book, I took these notes directly out of that. All right. So again, we're going to start out with particles. That's the main overall topic. And then we're going to do kinematics. Right, so this is all just the geometry of motion. So we have to define a couple key things in here. One of the things we have to define is position. Okay, and so we'll get into what coordinate systems are and stuff like that in a bit. But you have some sort of coordinate system. We have an origin to that coordinate system, right? That's kind of shown right here. Okay, and then we have to define position in that coordinate system. Right? And so there's a vector basically that goes from that base there. We're going to call that position R. And it's going to be a function of time. So this, by the way, is a path that particle is traveling along. Right? So there's a particle right here. It's moving along that path. And we're going to define position right at the beginning. That position is going to be R as a function of time. A short time later, over here, this vector right here, this position over here is going to be defined as R of t plus delta t. So some short time later, it's going to be over there. Okay. I always really like in engineering when they pick variables that don't make any sense, right? Oh, we're going to call the position R for all the R's in the word position, right? You'll hear me use that joke a lot. I like that one. And with my jokes, as long as I find them funny, I'm going to keep using them. Okay, even if you don't laugh at him ever, I'm still gonna do it. I'm tenured. It doesn't matter what you guys think anymore. I just as long as I'm having a good time up here, that's all that matters. Delta R, that vector that defines the change from one position to the other is going to be delta R. It's going to be R of t plus delta t minus R of t. Okay. And so we're kind of gonna use these terms in our definitions of acceleration and velocity. But you first have to define position. There's position. We have this new vector now that's called delta R, which is the change in position, right? What velocity is going to be is the change in position over time, right? And so under velocity, let's define velocity. This one makes sense, see, V, right? V for velocity. V of t is going to be the limit, like in mathematical terms, it's the limit as delta t goes to 0 of delta r over delta t. You've seen that before. That's the definition of a derivative, right? How does position change with respect to time as delta t goes to 0? So as that delta t becomes really small, it converges on that derivative. Again, this is the definition of a derivative, so we can call this, it is the derivative of the position. Be careful with my r's and my v's here. dr dt. Okay. That is what velocity is. It's the derivative of the position. And then in shorthand, we're going to write this as with a dot on it. Okay, that dot refers to saying that it's going to be a time derivative. Over here, I'm going to make a little note for you because we're diving into mechanics here. Note, the dot denotes time derivative, where prime denotes spatial. This is where we're becoming mechanists here, right? You took statics. You probably didn't do a lot of derivatives in statics, right? But in mechanics of materials, you're going to see a lot of derivatives taking place, right? And in those, in mechanics of materials, the shorthand, you're going to use primes because you're talking about taking derivatives with respect to x and derivatives with respect to y. That's what I mean by spatial. You take derivatives with respect to x and derivatives with respect to y. In mechanics realm, you denote those with a prime, right? Because those are spatial derivatives. In dynamics, most of our derivatives are going to be associated with time. And so in that case, we're going to do those with dots on them. So if you've ever wondered the difference between those, that's what it is. Okay, you see a dot on something, usually that's a derivative with respect to time. Sometimes you see a mixed, right? When you go into vibrations, those of you that are mechanical engineering, go into vibrations, you're going to have an equation that has both of them. That's going to have changes with respect to time and changes with respect to x. You're going to have both of those things mixed together, right? When you talk about multiple degree of freedom systems, you'll see those. And then when you see those, think of me, okay? In the future, you'd be like, oh, vibrations. Dr. Barry told me I would see these one day, okay? Just for me, do that for me. Okay. All right, one other comment. I just want to write one little thing. Velocity. Come on. Come on. Yep. Velocity is always tangent to path. If not, you're not on the path. That's deep. That's a deep thought for you today. Okay? Velocity is always tangent to the path. If for some reason velocity is not tangent to the path, that means you're not on the path. Right? You have to be your speed or your velocity has to be going along that path. If it's not, then you're not on that path. Right? So that's just a little side note there. Deep thought for you going into the weekend. Okay, now let's define acceleration here. A of t is equal to dv dt. Right, you could also do it in more general form, just to say it's the limit as the velocity, or the limit in the d delta v over dt as dt goes to 0. But we'll just jump to the derivative of it. A of t is dv dt. Again, you can write this in shorthand with a dot on it, right? Or it's equal to the second derivative of the position. So you can put 2 dots on there, meaning that that's the second derivative. Okay. Cool. I mean, we always have to start out with that. So we're going to use these definitions throughout the semester. Okay, this is the most general form of them. Okay. Right? Note that no forces or anything have been discussed yet, right? Those come in later when we do kinetics. Kinematics, again, is just geometry. All right, frame of reference and coordinate system. These are some key concepts that books spend quite a bit of time talking about these things, okay? And I always like to kind of discuss these first from like thinking about an airplane and then 2 people on that airplane. These are nice drawing here. Playing frisbee on an airplane. Probably should not do that. And if we were doing that, I'm throwing this frisbee from one person to the other, right? This is just a good way of discussing like frame of reference and coordinate systems, right? If I was on this airplane and I was playing frisbee with my buddy, with one of my sons, let's say, right? And I'm throwing them the frisbee. Like, how fast is that frisbee going, right? It depends, right? Like, what am I using as the frame of reference? Am I using the airplane as the frame of reference, right? That would be a good frame of reference for playing frisbee, right? It's like, okay, you know, you catch this, right? It's traveling 1 foot per second or whatever as it comes towards me, right? Like your frame of reference would be the floor of the airplane, the cabin of the airplane, right? But is that how fast it's actually going? No, right? Because like it depends if I use my frame of reference the Earth, right? If I was down here on the Earth, I'm going to draw it round. I know that's controversial in some arenas, but it is absolutely round. Okay, what if I'm looking up there at it, right? And I'm like, oh, okay, well, how fast is the Frisbee going if my frame of reference is the Earth? Well, 500 miles an hour plus the 1 foot per second, right? Like it's really booking, right? So yeah, you're just gonna be really careful about that frame of reference. But do I say that frame of reference that the Earth isn't moving? Son of a bitch, right? That's moving too, right? So like even to say that it's 500 plus 1 foot per second, that's not right either, because the surface of the Earth is, rotating around the center of the Earth. Well, so I'll just pick the center of the Earth as being the reference frame. Shit, that's moving too, right? I mean, if you believe in all this stuff, right? But like the center of the Earth, right, is rotating around the sun, right? Like it's projected around the sun. Well, let's just pick the sun as being the reference frame. Well, shit, that's moving too, right? Like that's moving too. It's moving around the center of the Milky Way galaxy. Well, the Milky Way center of the Milky Way, that's not moving. Well, that's moving too, right? In fact, we don't know what's not moving, right? That's a deeper thought for you, right? Like maybe one of you is not moving, right? Like we don't know, right? We have no idea. There's no way of telling what it is that's moving and not moving in the universe, right? Which is deep. It's a deep, deep thought for you, okay? But that doesn't matter. For most part, the frame of reference that we're going to use is the surface of the Earth. Like for the type of problems that we do, it's like this right here is not moving, right? For the type of problems that we're solving, it'll be that. But just be careful about that frame of reference, because you can pick. There are wrong answers necessary, and if what you pick as a frame of reference absolutely affects how you solve the problems. Okay, and like I said, for the most part, it's just going to do that. There's some later on stuff, like if you're talking about something going to orbit, you absolutely take into consideration that the Earth is rotating, right? If you're predicting storms and hurricanes and stuff like that, absolutely you care about it. If you have intercontinental ballistics, absolutely make sure that you have a frame of reference that takes into consideration the surface of the Earth moving and stuff. So we'll go from there. Okay, so let's just quickly say frame of reference, right? Baseline, right, is what we use as a baseline. Typically, what we assume to be not moving, right? Which can be hard. Well, I'll leave that out. This is getting too deep. We'll just say that, which we assume to be not moving. So we kind of covered that. What a coordinate system is, finger, is specific. There's lots of I's in there, so I was having issues with my finger. Specific set of coordinates within reference frame. Right. A specific set of coordinates that within a right, and then in there, inside your reference frame, you'll set an origin and things like that. Okay. And you have different types of coordinate systems. Right? There's Cartesian. That's everybody's favorite. It's my favorite. Cartesian. We have polar. Sometimes polar's better. And we have this one you may not have heard of before, but normal tangent. And in fact, we're going to use all of those in our solution methods, because again, sometimes depending on what you're talking about, sometimes those are better. Right? It actually makes the problem easier to solve and possible to solve. Okay. Again, the book's got a section on this. If I'm moving too fast or whatever, just give me a shout and say, go back to that. I wasn't ready yet to move on. Okay. What did I do with... Oh, I was going to show you something here. I'm putting stuff in weird places here. Oh, I was writing in my blank. Okay. So here's the deal. This I was pretty proud of. Yesterday I was sitting around, and I was like, when I was talking about reference frames, I was sitting in my office yesterday afternoon, and I was like, okay, let's see what the book has to call it, what it has to say about reference frames. okay? And so this came out of the textbook that you don't actually have yet, but it came out. I copied right out of there, right? So if you observe people in a room, such as a group or party, you can perceive their positions relative to the room. For example, your people can be back of the room and some in the middle of the room and so forth. The room is your frame of reference. To make this idea precise, we can, right? So it goes through this definition, stuff like that. And for whatever reason, I was like, does anybody play with ChatGPT? Have you played with ChatGPT? You should play with ChatGPT, okay? It's a good friend of mine, okay? I absolutely use it for everything. There's mixed reviews at the university about whether or not we should be promoting ChatGPT. Absolutely use ChatGPT when you can, okay? I'm serious. I love this thing. You haven't opened up the website before and been like, yeah, you have. Yeah, damn right you did, right? Like once you use it, like I was like shocked, right? Like last year, while the students were taking an exam once, I was like, oh, let me just mess with this a little bit, right? So I was just like, tell me a story. That's my first thing I told her. I was like, tell me a story about a structural engineer that falls in love with the building that they're designing. Right? And it put together, I mean, I was weeping at the end. It put together the most beautiful one-page story about this. There's like, oh, this girl grows up enjoying building Legos and blah, 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 and then works her way through the university system and excels and then designs this building and watches it grow from like, from the very base of I mean, it has all these details in it that from the, maybe I'll post it online. You guys could read it too. And from like, the foundation all the way to the top and how the wind would would blow through the beams and the sun would be setting and stuff. And then the way it ended, just on its own, was it said that she fell so much in love with it that she knew she would never be able to part from this building. So she bought an apartment within this building so that she could be with the building and the building could be with her. And I was just like, just crying. But I was just like, holy shit. And then I started going crazy. I was writing love letters to my wife. I was making poems. Like you can have it do anything. And then afterwards say, make it rhyme and it'll turn it into a rhyme as part of it. I mean, I swear to God, it does everything, right? I taught a coding class last semester, right? And all I really taught them how to do is tell ChatGPT how to code, like to what to code, because it'll do all of your coding for you. I've never coded Python before in my life, but I made an asteroids game that is magnificent because you just have a conversation with ChatGPT. I was just like, hey, I would like to make asteroids game. And then it goes, here you go. And then you paste it into Python and then it works. But then what I didn't like about it, I was like, man, I can't move, my spaceship doesn't move. And it goes, okay. And so then it goes, take this code and replace this code. And I did it, and then my asteroid moved, or my ship moved. But then, I don't know if you ever played asteroids before, but asteroids, the ship is supposed to have momentum. Once it's going in a direction, it's supposed to keep going in the direction, even if the boosters are turned off. And so I was like, hey man, like the spaceship doesn't have momentum. And it goes, sure, I'll take care of that. Boom, copy, paste, my ship has momentum. But it fucked up. Okay, because my momentum would go like this, but if I turned to the ship, the momentum carried around the corner. So I said, hey, you're messed up on the momentum. It shouldn't change when I change the ship direction unless I have the boosters on. It goes, oh, you're right. And it gave me new code, and then now it didn't do that. I swear to God, that's all I said to it. Just like, look, actually. And then it got that right. It's like, you nailed it. And then I was like, you know what? I would like little boosters to show out the back end of my spaceship when I press the space bar, when the thrusters are on. Boop, beep, boop. Did it. Right? And then it was like, you know what? I don't have a scoring mechanism. Could you add scoring? And then it fucking adds scoring. I swear to God, it does. And then a timing mechanism, like you literally just talk to it. If you're in computer science, whip that shit out, right? Like, I'm serious. Never once coded in Python before, yet I'm coding this stuff. It's really good at that. I will say, I tried having it solve dynamics problems. Like I just took problem statements and I said, here you go. Like your homework, for instance, I put it in there. It couldn't do it. I'm sorry to tell you this, but it couldn't do it. It has like writing and doing code, it's magnificent. But if you actually try to have it analyze something, it breaks down. And a classic example is somebody had it once. They were like, oh, if it takes 2 cars 5 hours to drive from San Francisco to LA, how long does it take 4 cars, right? And then it really messes that one up, right? It's like, oh, well, I got this, right? Hours per car, and then, it's like, you did that one wrong. But be very careful about having it analyze anything, but putting down like a rough draft of something that you want to write, all of my letter of recommendations straight out of ChatGPT now. Straight up. I'm serious. It is, all like, I was editing a student's thesis, and I get down to the final chapter, and like what he had as his main conclusions, I was like, that's not really what you wrote about. So I just took that chapter, like one of the chapters, and I put it into ChatGPT. I said, could you tell me what the main conclusions are? And then it goes, it gives me like a bulleted list. I swear, what kind of like Gen Zers are you? You're supposed to be on top of this shit, right? Like you're supposed to be like on top of these computer stuff. Okay, so what I did, this is one of my favorite things to do with ChatGPT, is I took this statement, right? And I said, hey, ChatGPT, would you please put this in Gen Z slang for me? So that you guys can understand it. So here you go, guys. This maybe you'll like it a little bit better, right? Yo, peep this. If you're vibing in a party and you scope out the room, you'll clock where everyone's chilling. Like some peeps might be in the back, others in the center. You get the gist. Think of the room as your viewpoint. To get all technical, imagine we slap a grid on that room like the pic labeled 13.18. You could pinpoint where someone's at, like where their core is, based on the grid. That's your go-to map for everything in the room. Now switch it up. Say you're on a plane, right? That's what I used, right? Everything you see inside is based on the plane's layout. Inside of the plane's your new viewpoint. Isn't that funny? That's funny stuff. So I think I'm going to try every announcement I post on D2L. I'm going to do it in Gen Z slang for you, so that you guys can feel it out. Yeah. Yeah. What's that?
It's not a joke.
It's not a joke. I'm going to do it. Absolutely. Absolutely. Right. It's so funny. And what I do, one of my favorite things to do is when I text my sons, I put everything into I put it into ChatGPT and say, please put this in Gen Z slang, and I send it to them. My favorite is bussin'. I think bussin's my favorite. But what is it? What's the no cap? No cap. That's the one I'm trying to slip that in where I can. Yeah, because I'd like to think of myself as being one of you guys, right? I'm just a college kid like you guys, right? Like, I mean, absolutely, right? What are you laughing at, Sally? Of course, like, I'm just cool and hip like you guys, right? And so I got to try to slip in some of the slang so that you guys don't know that I'm not cool and hip, right? And so I tried to slip it in. I was using that slaps quite a bit, but I think that might be out of date now, is it? That slaps. No cap. No cap. That's out of date. Okay. That slaps. Okay. Okay. Hold on. I just gotta. I mean, I have ChatGPT 4 because the university pays for it for me. It is awesome. It does really well. Yeah. In the coding class I taught, I had a couple assignments that I made sure that ChatGPT couldn't do it, and the amount of people that I had come into my class for like help that week was just like magnificent. But it's because all semester they've just been using ChatGPT for the whole thing. Let me just give you an example. I'm gonna have it make me a haiku about learning mechanics at Montana State. Let's see what it says. I'm hoping that it doesn't think that it's mechanics like we're. Oh, here we go, see? Montana skies vast. Mechanics secrets unfold. Bobcats learn and grow. Fire. No cap fire. No cap fire, right? Isn't that sick? That's all I said. Haiku about learning mechanics in Montana State. It knows that Montana State is the Bobcats, slip that sucker in. It knows that we're the Big Sky, slip that sucker in. Mechanics secret unfold. Son of a bitch, I got chills. I got chills going up, right? Play with it. Like, that's your assignment over the weekend, is open a ChatGPT and play with it, right? We had this discussion in our faculty retreat, and there was like half the faculty were like, what are we gonna do about this ChatGPT and people using it? And I was like, show them how to use it, right? Like, because I was like, do you not use it? Like, why don't you use it, right? Like, I mean, has everybody been like, it was a somewhat heated discussion. Like, well, they're not going to learn how to write. I was like, well, they don't need to learn how to write because ChatGPT will do it for you, right? And it comes literally. My true feelings on it is it's here to stay. Like, once you start playing with it, it has limits, but it is super powerful for stuff. And I went to a conference last summer, and a guy got up and said, hey, will AI replace you as an engineer? And the guy was like, no. But an engineer that knows how to use AI will replace you. And I am a huge believer of that, right? That's a tool. It's like, it would be like back in the day when they invented calculators. They're like, what are we gonna do? How can we teach math now that there's calculators? Well, how about we teach them higher level math where they don't get bogged down with, like, you know, why don't they get bogged down, like get them bogged down on these like really specific things? Have a tool do it for you. Have a calculator solve that for you. Have ChatGPT put down the rough draft for you, right? And then you can refine it after that, right? It is beautiful. Learn how to use it. Absolutely. Start going on it. I mean, don't use it too much. Like, obviously, still learn the writing and stuff like that yourself. But it is great at lots of things, and use it. Right? I don't know what you do for citing it. That's a little bit like I know that one journal specific. People were putting it down as a co-author. ChatGPT was my co-author on these things, right? Which I guess is I guess that kind of works. And then or you cite it and say that you used it as references and stuff. But I mean, like, my son used it on his science fair project. We were like, oh, he was doing how controlled burns affect things. He's in the 7th grade, and we're like, well, I don't know, what are the control variables? And we looked all over the internet and couldn't find like what the dependent, independent variables were for these things. And so we asked ChatGPT, and it was like, nice, beautiful list. It laid it out for us, and we're like, what's a good experiment? And it goes, how about this? And I was like, that's a great idea. And then, and with that, I mean, it is, you might as well do it. So be careful, because you might run into one of those professors that are like, don't ever use it, right? But in my world, freaking use it. Absolutely. There's something, I was gonna give you another example of what I've done with it, but anyways. Oh, that's what it was. If you've ever written anything in LaTeX, have you ever heard of LaTeX? It's a coding language for it's for editing documents and stuff, right? Typesetting documents. And I wrote my thesis and stuff like that. ChatGPT knows that. So a lot of my notes, like in that coding class, I would say, help me put together notes for this particular topic. And it would do that and lay it out. And I was like, okay, now put it in LaTeX code. And it would do it. It would format it in LaTeX code for me so that I could copy and paste that into LaTeX, and then I would run it from there. It's beautiful. Maybe I'll write a textbook completely in Gen Z slang for you guys, so you guys get it. You guys are Gen Z, right? It's Gen Z, aren't you? I think so. I'll ask ChatGPT later. But cool. All right, that's all I got for you today. We'll start with this 1D motion stuff on Monday and keep cranking it out.